And there we go. Okay, guys, thanks for being here today. Once again, I'm Alberto, and this is my very first webinar. I hope you enjoy it. As usual, this contains a massive amount of concepts, and in this time also, we will be enjoying a fair share of math. A lot of formulas. So the only prerequisite in order to be able to follow through is to having having attended to a scientific high school. So you have to know what is a derivative. So what is a partial derivative? A derivative. Don't worry, because I will be making a very quick recap in case. If you want to ask questions during the lesson, please do. I'll try to handle them as soon as I receive those, because I like to actually have everybody following through. So, as I already said, this, as you already know, because you are here, this is part of a webinar series which is hosted by Codemotion. Codemotion is, for those who haven't not joined yet the conference, is a very big tech conference, which is European-wide. It has a lot of locations like Madrid, Milan, Berlin. The upcoming event is going to be set in Milan. And also they are open for the call for paper for next year. From my personal experience, I can say that Codemotion is a really fairly organized conference. What I mean is that when you see the program, everything happens at the exact time it's supposed to happen, in the exact way it's supposed to happen, and everybody is always very kind. The communication is always very informative. So it's really a good place to attend if you enjoy being at conferences. Okay, so of course, visit their platform. It's codemotion.com, where you find all their news from seminars and upcoming events. So now let's get started with the current topic of the day. Today, we are going to talk about the mathematical foundation of the backpropagation. I'm sure that all of you, since you're here, have at least heard this expression, the backpropagation, as a mechanism which is involved in training, especially deep learning systems. So we use backpropagation to actually tell our neural network, but this is not only limited to neural network, but to any linear classifier, when is it going wrong. So today, but I'm sure that a lot of people don't really know how it works under the hood. So today we are going actually to explain that. For those who have never attended to a talk of mine, which is lately has been hosted at Codemotion, I'm a 36-year-old engineer with more than 10 years of experience. I've attended to I'm a software engineer. I've attended the Master Computer Science university course. I spent most of my time as a startupper. Lately, I've been working for a consultancy company, which is called SourceSense. And we do consulting based on open source technology only. So we only talk about stuff which you can download for free on the internet. I serve as an SRE, or as a DevOps, as some of you may say, and as a machine learning consultant. So Kubernetes, everything about continuous delivery, Cloud, Hadoop, Python, and stuff is all fair game to me. During the day, at night, in the last bits of spare time that I can afford, I usually headbang at metal concerts. So today, the outline is going to roll as follows. So we first start talking about the need for optimization. So why we need to optimize a function. And how we're going to do that by using gradients. Then we'll be introducing the computational graph framework and the backpropagation technique, of course. And then we're gonna talk really lengthy way about this 2 points, and then we'll be discussing about how the graph actually influences the flow path and why different architectures have different flows, have different difficulties in the flow of the gradients. And then I'm going to show you some actual code in popular libraries about where you can find examples of what we talked about. A lot of the concepts in this presentation come from the course the CS231 by Stanford, which is a computer vision with deep learning, and it's held by 3 wonderful instructors, which is Justin Johnson, Serena Young, and Fei-Fei Li. And Fei-Fei Li also is the author of ImageNet, in case you don't know. And these 3 guys are really rocker, and they really explain and expose a lot of concepts, a really hard concept, in a very simple way. So please go attend the course. It's free, it's on YouTube. It's really, really nice source. So let's start with the problem so far. So we have a data set. We have gathered a data set, and which is the training samples we'll be using throughout our training. Then we have a score function, which is a function which takes parameters, its weights, and the input. And just in case you didn't get it yet, this is your neural network actually, okay? And then we have a loss function. A loss function is a thing that actually provides you a score, a representation of how good or bad your classifier, your scoring function is actually doing against input samples. So during the training, we define the parameters W, the weights of my neural network, or my classifier. And it's really important to find the best W that actually defines the best classifier possible for the problem we're trying to solve. So how can we find the best W, the best weights? So the idea is that we use optimization. And optimization in this case revolves around changing the parameters, jiggling the parameters just a little, see how the loss changes, and if it improves, keep going in a loop until actually the improvements start to fade out, and we cannot go any better than this. And this, in that case, the training is over. So it reaches a convergence point. A classical intuition that it's always produced is the idea that finding the best W by taking a step, seeing where you are, and then keep going or going back where you were, is actually the idea where you are over the slope of a mountain, and you need to reach the valley. But it's like it's night, you don't know where the valley is actually. So you're not informed, but in this picture, you are informed by your sight. You know where the valley is. You just have to head towards the valley. But in the case it's night, you're actually lost on this mountain, and you need to find the valley. So an idea is that you could just keep walking by following the slope. So when you reach a flat field, then you know that probably you're in the valley. If you keep walking and the terrain starts to rise again, maybe you're going out of the valley towards the next mountain. You should actually stop because you're going out the optimal point. So this is all nice in the intuition, but the idea is that we are using mathematical functions because our scoring function, our neural network, is actually a mathematical function. Again, I would like to stress the concept that neural network should not be approached with the idea of a brain, but we actually treat them, all of them, as mathematical function. And once again, I would like to repeat a concept that I already stated in the past in another talk. Neural networks are a class of mathematical function in which we stack together one top of another an array of linear functions, and we sandwich them with non-linearities just to avoid that all these linear transformation collapse one onto another. And that's why it makes them so effective, because each linear function is able to model a part of the problem. We stack them all together, and we use it like an ensemble of it's really inappropriate maybe talking of ensembles, but it's a way to actually use a collection of stupid functions and to produce a very complex one. And following the slope, when we talk about mathematical functions in one dimension, is the derivative. So the derivative, we know, we studied that at high school. We know the derivative is an operation that provides you with the slope of a tangent. A tangent to a function tells you if the function is going down, or is a flat, is going horizontal to the x-axis, or if the slope is positive, the function is going up towards the infinite positive. And in multiple dimensions, the gradient is the vector of derivatives along multiple dimensions. So since we have multiple axes, we take a partial derivative, which means that I just take into account the contribution of that axis in the outcome of my function, and then consider all other axes as a constant. You could actually think about when you're stretching an image with Photoshop. If you stretch vertically an image, actually, you are just modifying the vertical axis, but the horizontal axis stays the same. So if you take the contribution of the x-axis in a vertical stretch, it's nothing, because horizontally the image did not change. And that's precisely what we do when we take the gradient of a function. So the slope in any direction is the dot product of the direction with the gradient. So when we actually take the derivative and we apply this the gradient with the direction, we obtain a slope which can be positive or negative. And the direction of the steepest descent is the negative gradient, actually, because you're going down. Okay? Let me check if there are questions so far. Okay. There's nothing. There's nothing. Okay. So let's just take an example about what does it mean to jiggle the parameters and trying to find to optimize this function. So on the left, you can see the current weight. The current weight is a vector or a tensor or a matrix, actually. And we can see that all these values of this tensor actually, and when plugged into the loss function, give us this number, this absolute number, which is the loss. The lower the loss, the better. The higher the loss, the worse our model is performing. So if I try to change my parameter just a little, so just in case, please guys, try to remember that the derivative is the function itself plus a very, very small number. Then we subtract the original function, so we take only this very, very small difference divided by the small difference itself. What we obtain here is not 1, of course, but it's really like the angular coefficient, the slope of a line, which is of a linear function, which is passing through two very, very close points. And this is actually what we do here. So we just add this very, very small number to this parameter, and our loss changes a little, of course, because the loss is a function of our weights. So if I change the weight, the loss changes. And then I take the derivative here. So this is fx plus our very small quantity h, which is this 0,0001. Then we subtract the original function, and we divide for that small number. And what we obtain here is the gradient of this of this function to the total loss, which is the contribution of the parameter we changed to a total loss function for that very, very small jiggling. If we do the same, we change another parameter and the loss function changes again, then we have another number, which is the gradient of this line. We obtain actually a gradient for value, the derivative for respect to one of each parameters that compound the full weight. So we take, it's like all of these are different axes. Usually we are used to think in 3 axes, in 3 dimensions, but all of these numbers are dimensions of my matrix. All of these are parameters, and all of these contribute to the loss. So we take the derivative respect to one line, one after another. And then we keep doing like that, and each time we jiggle a number, we know the loss changes, and we measure. If you want to keep the loss down, we want to go into the direction which puts our loss down, we actually need to change our parameters following the gradient, and the gradient must be negative, or at least it must change in a way that brings our loss down. So in this case, jiggling this parameter actually yields the very same loss function. So the gradient is 0 because this parameter did not contribute to the change of our loss. We change this number, nothing changes. So this parameter is actually like a dead parameter, and the gradient is 0. If we change this parameter by just a little positive, our loss function goes up, so the gradient is positive. And if we change this parameter positively, the loss goes down, so the gradient is negative. And we should actually try to increase more this parameter, because this parameter brings the loss down consistently. And we should not increase this parameter, because when we do, we actually bring the loss up. Okay, so we just go and try to do this over and over again until our loss goes down. And this really, although it works, is actually called the numerical gradient, because we try to use a numerical calculation. This is really silly because it would be super slow and super inefficient. You have to think that a medium-sized neural network has tens of millions of parameters, and you cannot go around jiggling each parameter one at a time, because your training will last for months. Instead, since the loss is just a function, so you can see here the loss is a function of the single contributions of all the outputs plus a regularization term, which is actually a function of the weights. And the single contribution is actually, here we can see a hinge loss of a support vector machine, is actually a function of the scores of my classifier and the scores of the original I was expecting. And the score is also a function of my weights. So everything is just a function, mathematical function of my weights. So we can use the calculus to compute the analytical gradient. What we want here is the gradient of the loss in respect to the weights. This symbol is called nabla. And this thing can actually be done with numerical calculus. The analytical gradient actually does it in one pass. Okay, so if I take the derivative of this function, instead of moving manually the numbers, I take just the derivative of the function with respect to all these variables, I obtain a single pass all the gradients. The gradient descent is a technique where we apply iteratively a fraction of the gradients to the weights, and then we try to take again a derivative. And we do that over and over and over again until we obtain almost 0 to all of them. There's a problem to this. Although this technique works and is much more efficient, let's just check out if there are questions. Oh, wait a second. Are we forced to add the same quantity H, or are we able to subtract, add in a random way? Well, you should actually, okay, there's questions. You should actually add the same quantity, because the same quantity must be really, really small. It's a quantity that tends to 0. So if your numbers are like a float, for example, float 32 bits numbers, you should actually add the smallest numbers you're able to. So, and you should do that the same to everybody. It must be just a small number, because in this way you can actually obtain a better estimation of the gradient. It's not rough. Okay. Also, let's just in order to explore different direction. I don't get it. Okay, we decided there. Okay, I'm saying to add the randomly plus minus. No, always consistently try to add the plus, because otherwise you're not exploring. You're exploring different directions, but you are doing it in a randomic way. And the idea is that if you consistently add, then you are able to consistently make a decision about whether you should go up or down. You always try to walk of one step and in front of you if you're walking in a mountain, and then you measure. If the first time you walk forward, then you walk on the left or on the right, you're not using the very same action to yield the outcome that then you want to measure. So you have to be consistent. Okay, you get my point. Join a bit late. Can you please tell me how did you calculate the loss? Where I calculated the loss. Yeah, if you mean in this example, it's just a function that you're not interested in. Is any arbitrary function. The idea is that we want to see the effect of changing a number over the loss in this case. Okay, the loss is given like the parameters. I hope I answer your question. Okay. So the idea is that doing with the derivative actually is a huge boost, and it works. It is approximate, but it works very well in practice. But the problem is that you have millions of these parameters, and end-to-end gradient analysis is actually impractical, because you cannot just go around and calculating the gradient for all the weights in your neural network, all of the same in one. Why? It's theoretically possible, but your networks tend to be really, really large. So, for example, on the left, you can see a narrow Turing machine, and each line here is a tensor, and each balloon is a matrix, is a transformation, is a linear transformation. So there is a matrix of weights, which can be of thousands or millions of weights in just one balloon. Then there are the other balloons. If you take the derivative all at once, it will be really, really impractical to do that. You can see also here on the left of the right upper corner, this is just one level of an inception module. And this thing is actually 27 or 22 deep. And all of these are matrices. And here we have ResNet, in which each square here is a matrix of layers. And this thing unrolls for 135 layers in the ResNet 135 version. These are 34 layer actually, but it can go 5 times fold. So actually you need a way to factorize the complexity of such a huge operation, because taking derivatives of millions of parameters at once is really impractical. And now we take the chance to actually introduce the solution to this problem, which is the computational graph framework. So in order to compute gradients for an arbitrarily complex function, we unroll the function as a graph of operations. And then we iterate. So for example, in this case, I'm showing you the loss. This loss here is actually the result of this R, which is the sum of these weights, you can see here, and it's a function of the weights. Then you have the loss Ly here, and Y is actually a function, max, which is actually a function of Wx. So you can see here that starting from the single operation, I built a graph in which each operation is actually a step. It's like a node in this graph. And the idea is that once we have this graph, we can use a technique which is called backpropagation in order to calculate the contribution of all of our weights to the result of intermediate stuff. Okay, so just wait a second. All right, so just wait a second because there's something here, and okay, no, okay, wait, everything's all together. Okay, I didn't recognize the one slide. I thought it was something else. Okay, so in this case, let me just show you how the backpropagation actually works in this case. So we have a function, a very simple function, which is a function of 3 parameters, x plus y and z. And we have 3 numbers, which leads so -2, 5, and 4. And we want the result. The result obviously is -12, in which we have 5 and -2 is 3. 3 times -4 is -12. Okay, and we want to take the derivative of f in respect to x, y, and z. Okay. So just as a reminder here, I would like to I put here the derivative of the small functions. So when you have a summation of 2 variables, when you take the derivative respect to just one of these variables, everything which is not the variable becomes a constant, so it goes to 0. And then you take the derivative of this thing, and then you actually subtract 1 to the exponent. So x is actually x to the power of 1. If you do x to the power of 1 minus 1, turns to x to the power of 0 and becomes 1. So the derivative of q respect to x is actually 1. And the same holds, of course, for the y for the same reason. This goes to 0 and this goes to 1. And this is to say that when you take the derivative of a summation, the gradient actually transfers without any discount. Is actually discounted of 1, so it's not discounted, it transmits. And when you have a multiplication, taking the derivative of one of the 2 variables, actually, q goes to 1. And since z is a multiplier, so the derivative of f with respect to q is actually z, because this goes to 1 and what it stays is z. Z is not actually cancelled because it's not added. It's actually a multiplicative factor. Okay, I hope that for most of you this is clear. So since we want a derivative, we start here. So we start taking the derivative of the result f. In f is actually 1, because the contribution of f in f is maximum, of course. This is a very trivial example, but just because I'm starting here. Then we move to z. We want to take the derivative of f with respect to z. So what we know here is that when you're taking the derivative of something, and it's a multiplication because it's q times z, the result here is actually q. So the derivative of f into z is actually 3. Here is the other variable, okay? And if we want to take, of course, the derivative of f respect to q, the result is z, and z is -4. So the gradient is -4. I hope that until here, everything is really, really clear. We just take calculating the gradient of q and z respect to f. We still have to get here because we want the gradients of z, y, and x. We're not interested in q. And here problems begin to arise because y is not connected to the f. So I cannot take directly the derivative of f respect to y. It's not here. It will go to 0 because there's no y here. Everything here will be treated as a constant, and it will be an error to do that. So what I can do actually here is to say, okay, epsilon doesn't, y doesn't contribute directly to f, but it contributes directly to q. So what I can do is actually say, hey, df over dy can actually be expressed as df over dq times dq over df. Here, actually, I have multiplied up and down for Q, so it doesn't change. But here I'm expressing a concept that the contribution of Y to F is equal to the contribution of Q, and this I can calculate, and then I have to calculate the contribution of Y to Q directly. So this thing is called the chain rule. So I iteratively calculate the gradient taking a single step back in the computational graph, and that's why we call it backpropagation. So I can calculate dq over dy. I can do that because here dq over dy is 1. So actually, what I obtain here is that the -4 gets copied over here, and same holds for the x. So now we have calculated actually df over dx, which is -4, df over dy, which is -4, and df over dz. And this is actually this number expresses the contribution in how we the contribution of the single variables towards the result. Okay, and we can do something, or well, if you differentiate without considering x plus y and q, then different with respect to y is possible, right? So if you differentiate without considering q, x plus y, then differentiate with respect to y is possible, right? And it's not really directly possible, I think, for the reason I expressed before, because if you take the derivative of f, and you just treat Q as like a black box, all of this would just go well. Of course, I can take the derivative of this thing. Yeah, sure, I can do that, because I can take just the derivative of x plus y, z x plus yz. I take the derivative of this, xz goes to hell. And it just says yz, and it turns out to be z. So actually, the -4 is what gets copied here. Actually, yes, it's possible, but try to think about this formula as a very, very, very long function, and you don't want to actually solve all of that for all the variables. So try to think as a function of 1 million variables, not 3, 1 million. And then you have to actually do the calculation to factorize everything in their minimum, no, not to factorize, to full express all the single factors, rule out those who don't contribute with respect to the current variable we are deriving against. And then you do the same over again iteratively for each single parameter. It's really rich, it's really, really costly. Of course, you can do this directly, this one. But we don't want to do that because your function may be arbitrarily complex. And instead, with this technique, we can actually do, we can get away with very simple local calculations. Okay? I hope it was good. Okay. Okay. Oh, okay. And the idea is that each node is aware only of the surrounding. So the contribution to the local computation, which is gradients, are local to the node. So here you have the z and the x and y, and you have these local gradients here, which is the contribution of x against z and the contribution of y against z. When you have your gradients of your loss function coming back, you can actually say that the contribution of x towards the big loss function is actually dl over dz, which is this one, and is known because it's the upstream gradient which is coming to you, times dz over dx. And what you obtain, taking this absolute number and multiplying for the local gradient, is actually you obtain the gradient of x, the exact gradient of x. And you can do the same here. And of course, this gradient you're going, this downstream gradient, may also be the upstream gradients of other functions. And you can go back and back and back and back in different layers until you go down and actually reach the bottom of your network. And this explains how you can get away with the backpropagation in a very, very fast way, because you can just do serially this thing, and then here you can parallelize. And that's where all of this matrix calculus in the GPUs, which is nothing else but a very big, highly parallel processor of the small matrices, can actually gets you very, very far with the boost of performance it gives you. So let's do a real one now. This is actually a one layer fully connected network, because you see that we have WX plus B, and here you can, what function is this? Do you know what it is? I think it's a sigmoid, right? Okay. Maybe it's cumbersome for you to actually answer through a question. So yeah, it's actually a sigmoid. And this is a single layer with a sigmoid. Here I have written for ease the derivatives of all the single functions that we are meeting here. If you unroll this graph, this function into a graph, you obtain something like this. So let's just start calculating respect to these parameters, the outcome here. So we start with this. Maybe somebody asked something. I know that function. Yeah, it was a sigmoid. And it's a function you should never be using, because it's super inefficient and ineffective. You should actually be using a hypertangent, tan edge, or maybe a ReLU, but not a sigmoid, because sigmoid suffers from a lot of problems. Maybe another webinar about the problems of the different nonlinear functions. So now we are calculating the gradient for the first transformation. So this is the upstream gradient, which is 1, and we want to calculate the downstream gradient here. So the local transformation is 1 over x, and we have to take the derivative to go back, right? So we take the derivative of 1 over x, which is actually minus 1 over x to the power of 2, x squared. So we do the upstream gradient times 1 over x squared. What is x? Is this thing, the result here. So we do 1.37 squared, and we obtain minus 0.53. Is this passage actually clear? What we're doing here is measuring the contribution of this number in getting this thing here. Since we went through this function, to go back, we have to take the derivative. And to take the derivative of the intermediate function is taking this thing and actually multiplying the upstream gradients for the derivative of the transformation to the local value that we had here. And we obtain the local gradient of this number towards the end number. Then we move one step back and we obtain a plus 1. Plus 1 is a function of adding a constant to a variable, and the derivative of this is 1, because when you add a constant and you take a derivative, the derivative is 1, because the contribution of the constant is basically the function gets away, and you obtain this is 0, so it's nothing, it's 1. Okay, so we obtain the local gradient here, 0.53 times 1. And this actually turns out to be something we could be expected, because when you have a sum here, the gradient always distributes evenly. Here we have a sum of a parameter. Here we have a sum of fixed number. So actually, it's like we have another branch here with plus 1. So we know the gradient gets just copied when you add something. Then we have our exponential function, and the derivative of this is doesn't change. So we have the gradient times the function, which is e to the power x. X is minus 1, so is times e to the power of -1 and is minus 0.20. Okay, no questions, good. And so the gradient gets discounted a little more. And then we have the multiplication for a constant. So in this case, we times -1. And when you multiply for a constant, not add, we multiply, the derivative is the constant itself. So in this case, we have the gradient times the constant, which is -1. And so you have 0.20, you just invert the sign. Then you have a sum here, and the formula is always the same, the upstream gradient times the local gradient. So the upstream gradient is 0.20, the local gradient is 1, because you are summing something, and then distributes evenly, it gets copied. And then you have the last one, which is a multiplication. So the local gradient times upstream gradient, the upstream is 1, the local gradient is the other number. So in this case is 0.20, for the other number is minus 0.20, and 0.20 for the other number is 0.40. This is because the gradient of a multiplication is always the derivative of a multiplication between two variables with respect to one variable is actually the other variable. Derivative of qx respect to x is q, actually. Okay, is there? Will be able to view an event or recording of this interesting lesson? I don't know. Actually, don't know. I hope so. I hope they're recording that. Maybe Joanna can actually tell us later on if they are re-recording something. I hope so. So until now, we have seen how the architecture changes the flow. So each time you have an AND gate, the gradient gets just distributed. It's just copied without being discounted. Each time we have a multiplication, the gradient is switched. So you have 2, 3, 2 minus 4, it gets switched. So the -4 is reflected over this one. So the lesser the numbers, here we are dealing with integer numbers for simplicity, but you know that in your deep learning matrices, these are all float numbers which may be very, very small. And that's why a gradient becomes thinner and thinner and thinner the further you go back in your matrix, in your network. Because if you have a very, very small float number, this number becomes twice a very, very small number. And then if you have another multiplication here, it gets multiplied for another small number. And so the idea that your gradient eventually fades away and you have the infamous problem of the vanishing gradient is actually due to this effect. When you have this max gate, look at that. It happens something really curious. You have a max gate here, and the gradient, one of the two numbers, is always 0. And the other one is simply copied. It's not a coincidence here. If you think about it for a second, it's actually pretty obvious why. Since this is a max gate, the max between 2 and -1 is 2. So the contribution of 2 over 2 is this one. -1 did not contribute, nothing. It was just taking a choice between the two. So the contribution of -1 is 0 and its gradient is 0 accordingly. So actually the max gate is a gradient router because actually it's like a rail switch for the trains to go left or right, and it gets switched in the routing term. So it gets routed in this way, and here is nothing. All this part of the network is basically dead, doesn't change. Its gradient is 0, so their weights will be changed up to 0. Please note that when you have a branch here you don't have any additive branch. You're just merging and merging and merging. But when you split, actually, you go in one direction and another. When you backpropagate, the gradients add. You don't subtract, you add. So you have 2, you have 3 here. The gradient here is 5, actually, because it's obvious, because This node is the single responsibility for everything that happens here and here. So if you have a loss here of a certain number and another certain number here, it's pretty much obvious that the contribution towards these two numbers comes from this one, and the gradient should be added back by being summed here. Now that you know how the different operations, being their max, multiplication, or summations, actually how they change the flow, now you're really able to understand why in the recurrent neural network, the LSTM, which is the improved version of the simple recurrent cell, and the recurrent cell is very highly subject to the vanishing gradient problem, and the LSTM doesn't explode. Why? Because if this is the internal schema of our LSTM cell, since there's this additive port, the gradient is distributed evenly here and here. Of course, this is the forget gate. So in case you activate the forget gate, you will not propagate the gradient to the previous cell, because you should stop here. You should forget the contribution of the past stuff. And this is particularly useful when you are parsing a sentence, for example, character by character, and you are rolling this LSTM cell over and over again. If you encounter a period, then you should actually, everything that starts after the period doesn't have anything to do with what you've seen so far. So you should not take into account for the next word that of the previous word. The cat is on the table, the cat jumped down. The second time I say the cat has nothing to do with the word table, because there's a period in between. So the period actually is learned by the STM as a forget gate, and the gradient doesn't propagate back. So the previous cells will not learn anything from due to the fact that the second time there was another the cat. Okay, so the gradient gets copied here. The gist of it is, and the LSTM is able to keep learning even if you have unrolled tens of times. You will not encounter a vanishing gradient problem. Okay, because the multiplication happens here, not here. This is just 1 or 0 actually, and the previous cells. Also, this also explains the highly effectiveness of ResNet. Why ResNet is famous for being 150 layers deep. Since we have here a sum, and then we have this skip connection, which is just a matrix with an identity. So the tensor coming here gets copied because the identity matrix is diagonal. So each number gets multiplied for 1 and the others go to 0. And so you obtain the very same tensor here. That's why the gradient, which is a number, gets propagated here without being discounted by the fact that it's passing through 2 different layers. And so since you have the residual connection, as long as you're able to copy the same number that you got at the source of the last layer here, you can go of unlimited depth, and the gradient will always flow back in all its pure form without being discounted by previous layers. And that's why it made these architectures are so effective. Okay, now you actually know it. Final words, I would like to show you how this is done in the code actually. So in the code, we take a modularized approach. And since every layer is a class on its own in object-oriented thing, in Torch, actually, you create a new kind of layer by extending the Torch autograd function class. And what you have to do is just provide the 2 methods. The first one is the forward method that gets invoked when you're doing the forward passing your network. So with a sample and you're predicting output. Then if you are doing training, with the output, you calculate loss and you backpropagate. And when you backpropagate in this layer, the backward function gets called. How can that be done? Simple, because you pass a context, which is your autograd tape, basically. where you store the gradients, and this is your the input x. So this is a very simple layer which just does an exponentiation of your input, takes the result, the local result of this cell, and saves that in the context. So it's kept in memory. And then you return the result for the next layer. When you invoke the backward, the context is taken from the list of saved tensors. It was stored in the context here. And your result is actually multiplied by the upstream gradient that is coming back. And this is the local number that will be generated and passed to the downstream cells. And it will be the downstream gradients of all the cells that came before you. And if you really, really want to dig in the code, this is an actual example that I took from PyTorch. This is actually PyTorch Cafe2 operator sigmoid ops_u. This is the CUDA code of the Cafe2 library inside the PyTorch project. This comes from GitHub. You can go and check. And if you dig into the CUDA C++ code here, you can see this is the sigmoid CUDA function. It's called kernel here. But the important part here is that this is the x, so this is the input. And you can see here that for the sigmoid, which formula I wrote here for simplicity, is 1 over 1 plus exponential of minus your input, which is the same here, right? This is the input, is the w times x, which is the input then to a sigmoid. And this is the actual number you get in, and this is the actual number you get out. So the outcome of the sigmoid. And this is the forward method. In the backward method, they call sigmoid gradient. So if you go into the cafe, you can see that all functions actually have a gradient. So a function, gradient, CUDA kernel. So this is the backward actually. And you can see that we are passing back the results, which is a tensor, and the gradient, which is another tensor. And the derivative of the sigmoid is the sigmoid times 1 minus sigmoid. The sigmoid is the output of this layer, so it's y. And you have y times 1, tensor 1 minus y. Y times 1 minus y times the gradient, of course. And then you can obtain the gradient of the inputs. And you can pass this back on. This is really procedural code. There's no return because you pass a pointer here and the pointer gets modified here. And when the function goes out, this pointer, this value, which has been passed through by pointer, the actual value gets referenced and it's actually modified the next time you read it. So you can really see how everything that we talked about is actually implemented in the CUDA code, right? So closing remarks, the bottom line of this seminar is that the neural networks will be very large. So the one way to get away with this is to factorize the complexity in local calculation without trying to eat the functions all in one go. How we do that? We do that through backpropagation. And the backpropagation is the recursive application of the chain rule along a computational graph to compute the gradients of all the inputs, of all the intermediate results, of all the parameters, with respect to all the parameters. The implementation, which is your framework in this case, maintains a graph structure where each node implements the forward and the backward API, and everything is kept in memory. The forward API computes the result of an operation and saves an intermediate result needed for the gradient computation in memory. So it maintains all this structure. It expects that each layer exposes the forward and backward API. And also the backward function actually applies the chain rule to compute the gradient of those functions with respect to the inputs, pulling that back from the vector of context, which is local to every node. And that's basically it, guys. So I hope you enjoyed the seminars, although it was really, really, really rich of math and a lot of concepts. I hope you really could follow me through. I hope to have handled all your questions. If you have further questions, please, you're free to actually write them in the chat. I'll be around here for still some minutes. Or in case you don't have any questions, I hope it's because you actually understood everything. And okay, so thanks, Giacomo. He doesn't have any questions, so I hope it's because you understood everything. Okay, guys, good. Thanks to all you guys. I hope you enjoyed everything of this lesson, and I hope to see all of you in Milan for the upcoming Codemotion on the 24th, 25th of October, in which I will be presenting my new talk over neural networks. We'll be talking about reinforcement learning and how we can train autonomous agents with neural networks. It was great to have you all, guys. So take care, and thanks a lot for joining again, and have a great evening and great weekend.